Okay, so now we are going to start with photoelectric effect. So the photoelectric effect is basically an example of particle nature of light. An example, a phenomena that is explained only by the particle nature of light and not by the wave nature of the wave model of light. We'll later on see that why it is said so that it is not explained by the wave nature and why only by the particle nature. So it is basically a phenomena that when photons or light is incident on a metal surface, it ejects electron, which leads to the photoelectric current. Now, to understand this phenomena, first I would like to uh, tell you about some terms. First of all, it is work function. So, work function is the minimum energy required to eject an electron from the metal surface. Second is the threshold frequency. So threshold frequency is the minimum frequency of light which is required so that an electron may be ejected from the metal plate. The third thing is the lambda threshold, means the threshold wavelength, that is the maximum wavelength the maximum wavelength of light for which ejected from this metal surface. So explanation again that photoelectric effect is the emission of electrons from metal surface. Now, um, now we can see why this phenomena is not explained by the wave theory, or we can say that discuss the failures of the wave theory in explaining photoelectric. So the first, okay. So the first thing is about intensity. According to, if we say that photoelectric effect is a wave phenomena, then we would be saying that the more the intensity, with more energy, the photoelectrons should come out. Means if the intensity is 2 and um, the photoelectrons are coming with say 5 electron volts of kinetic energy, then according to wave theory, if the energy of photon is increased, suppose to 5, then this value must also increase, but this does not happen. In fact, it is observed that um, only that the more the intensity of light, the more the photoelectrons are ejected. Means the increase in intensity is not increasing the energy of the photoelectrons, but it is increasing the number of the photoelectrons that are being emitted. And so this was failure. Second was about the frequency. So if we consider the wave theory, it would be saying that for any frequency of light, for any frequency of light, if incident on the surface, it must increase the energy of the photoelectrons, and thus, in some time, the photoelectrons must be ejected. But it does not happen so. In fact, until a particular frequency is reached that we called earlier the threshold frequency, until the energy of the light corresponds to the threshold frequency, we do not see any ejection of photoelectrons from this metal surface. Whatever be the intensity, it does not matter, but the photoelectrons are not ejected if the threshold frequency is less than the work function, which is the minimum, which corresponds to the minimum energy that must a photoelectron must have to be ejected from a metal surface. While considering the work function, we say that electrons are ejected without any interaction in the metal. You can see that if there are interactions in the metal, the electron would face difficulty in ejecting out, as it would be losing energy due to the attraction forces and the repulsion forces inside the metal atom. Thus, this is the minimum energy that is required for the ejection of a photoelectron, and it corresponds to the threshold frequency of light. Third thing is about time. As we say in the wave mechanical, the as it is said in the wave theory that waves travel in forms of wave front. That is, if this is the source, then these are the wave fronts, and these wavelets arises from these wave fronts. So the traveling of wave is kind of like this, as explained in the wave theory. But in case of uh, But in case of photoelectric effect, this theory does not explain the concept clearly. It does not even stand close to the thing, because in this it is said that if energy is ejecting out from this place, then it must travel in all the directions, all the possible direction, and the energy given to this place must be distributed uniformly. But in case of photoelectric effect, this does not happen. In fact, we say that photons are packet of light that are bound to a single electron, and if this is more than the threshold frequency or the work function, sorry, not the threshold frequency but work function, then these photoelectrons can be ejected. Now the next thing is about the maximum kinetic energy that a photoelectron being ejected from the metal atom can have. It can be given by Kmax is equal to h nu minus phi. H nu is the energy of photons that are being of the light that are being given to the electrons, and as we know, phi is the threshold, the work function. If you want to draw a graph of Kmax and nu, we can say nu is the frequency. We see that it would be a straight line, as it is a direct relation with nu. It would be straight line with the y-intercept of minus phi. And if this graph is drawn for any other metal atom for the same frequency of light, then it would always be parallel to this curve. Only the threshold frequency would be changing as the metal has been changed. Now, the next thing is about Now we would experiment a few things. Now we will actually conduct a photoelectric experiment. We would be having this tube. Inside there's the anode, and there's a small opening from which light can come inside. And this is the target metal plate from which photoelectrons must eject. This is the cathode. We're connecting it to a power source not for the sake of ejection of photoelectron but for conduction of the experiment. The ejection of photoelectrons is independent of the, photoelectrons will be, yes, the ejection of photoelectron would be independent of the uh, power supply. Now when this light is incident on the metal plate, electrons are ejected, and as these electrons are ejected, they form a cloud near to the anode. Why? Because due to this potential difference that has been applied here, it creates an electric field, and this electric field can be said to be directed as this is the positive, this is the negative. Electric field can be seen uh, to be in this direction, and as their electrons, so the force would be in this direction. Now due to this cloud is formed near to the anode. Now we would conduct some experiments. First of all, we take lights of different intensity. Suppose in the first experiment it was more than the second one and the same frequencies of light. Okay, first of all, let's plot the basic graph that we'll be drawing. We'll be drawing a graph of potential difference, potential versus the photoelectric current. Don't get confused with the intensity. It is the photoelectric current. So for the normal experiment, it can be drawn like this. This is stopping potential. Stopping potential is the minimum potential that is required for stopping any electron or for making the photoelectric current zero. That is, Vs must be equal to K max. Why? Because the maximum effort that we can put on any electron would be the one which is having the maximum kinetic energy. So Vs can be given by, sorry, it is EVS because you can see that there is a potential, now it is a potential energy. EVS is equal to half mv square, or we have written earlier K max is h nu by minus 5. So it's equal to h nu minus 5. So we get Vs is equal to h nu by 5. So h nu by E minus 5 by E. So we'll be drawing a graph between potential difference and the photoelectric current, and we'll see that this is the stopping potential. Sorry, this is stopping potential, and as the potential is increased, the graph would go up like this, and later on it will say this is the saturation current. And you must be thinking why this is a non-uniformly increasing graph. This is because of the cloud that was formed on the passage of current and the electric field. Now there's this potential where whole of the cloud has been broken. It's called the pinch potential. Later the current gets saturated. Now we will drawing the graph between photoelectric current and the potential difference in case when the intensity of the first light is more than the second one. As we know from earlier that intensity only leads to increase in number of photoelectrons that are being ejected. So due to this increase in the intensity, more number of photoelectrons would be ejected. So we can plot the graph like this. As more number of photoelectrons are being ejected, so the current that we would get will also be higher. As we know that current can be given by NeAVD, as Vd is dependent on the material A to E2. So as N increases, the number of electrons per unit volume, so current also increases, as we are seeing it right here. Second thing is that if the intensity of both the lights are same and if one is having a higher frequency than the second one, in this case it would be something like this, that as both the lights are having different frequency, so Vs would be different for both of them, as Vs can be given by h nu by E minus phi by E, as phi by E is different, sorry, not phi by E, nu is different, so Vs must also be different. So Vs1 and Vs2 as S1, S2, as the first is of higher frequency, so it would be from here, and the second one is from lower frequency, so it would be here. And we would observe that the graph is something like this. Yes, and I forgot to mention the point pinch potential in here. This is the pinch potential for the first one. Pinch potential for the first one would be, sorry, this is the pinch potential for the first one, and this is pinch potential for the second one. As pinch potential of the first one will be higher, why? Because the intensity is higher, the cloud would be bigger, and in this case uh, we can explain this one as the intensity is same, the saturation current would be same, but why is this so happening that they're meeting at the same point? The reason for that is when the intensity is increased, number of photoelectrons getting out is more. Also, the intensity is same. As the frequency is more, in the first case, we would see that the electrons coming out would be of we would see that more number of electrons can now come out from the metal surface. Yes, because the frequency is more, so more number of metal can come out. This means more number of metal electrons can come out at a certain point of time. Yes, at a certain point of time, as frequency is more. And this means that an electron inside will be struggling with these interactions, and as we have increased the frequency, more frequency the photoelectron must hit this one and it will eject out easily. Yes, so more number of electrons can come out now. Why? Because the frequency increase, so they can escape the interactions very easily. Thus we can see that the graph is like this. Now we can start with some past year advanced questions. The first one would be The first one can be started from here. Let me just change the pen. Okay. Now, as the first question says that some energy levels of molecule are shown in the figure, the ratio wavelength of lambda 1 and lambda 2. So, as I can see that in lambda 1, E amount of energy is inconsidered, and this lambda 2 corresponds to frequency energy of lambda E by 3. So, I can say lambda 1 corresponds to E, lambda 2 corresponds to E by 3. Now, as I think they are asking me the ratio of lambda 1 and lambda 2. Now, I will need to find the proportionality of energy with lambda. As I know, E is equal to Hc upon lambda. E is equal to Hc upon lambda. So, I can say that E is inversely proportional to lambda. Now I can say that E1 upon E2 is equal to lambda 2 upon lambda 1. So lambda 1 upon lambda 2 is equal to E2 upon E1, that is 1 by 3, that is the C option. Second question is this one. It is asking me that if an electron beam is accelerated by potential difference V to hit a metallic target to produce X-rays. If an electron beam is accelerated by potential difference V, okay, to hit a metal target to produce X-rays, okay, okay, the potential V to produce X-rays. It produces continuous as well as characteristic X-rays. From this, I understand that when the electron is moving, it would be having some interaction with the metal while it is moving, as well as when means I wish to say that the electrons while the, while it is traveling inside the metal, it is emitting these continuous X-rays, and it is also replaced some electrons, due to which it is emitting characteristic X-rays also. So if lambda minimum is the smallest possible wavelength of X-ray in the spectrum, the variation of log lambda minimum and log V is correctly represented by. So I need to find the relation between V and lambda minimum first. Lambda minimum is the smallest frequency wavelength of X-ray in the spectrum. Okay. So what I get from here is that I come to know that the kinetic energy of the photoelectron is EV. Now, second thing I come to know is that the minimum energy that it would require for emission of characteristic X-ray would be lambda minimum energy, sorry, Hc by lambda minimum, it would be Hc by lambda minimum, that would be equal to EV. Okay, lambda minimum must correspond to Hc by lambda minimum. Okay.